Now let's set the stage by drawing the Lewis structure for the ozone molecule O3. I recommend that you pause the video and try that now, and I'll give you a hint. Ozone ends up being in a straight line. Oxygen, then oxygen, then oxygen, not some sort of a fancy triangle structure. So go ahead and pause and try that one now. Now, I'll go ahead and start doing it too. We have 1, 2, 3 oxygens. Total of 18 valence electrons, which makes sense. 6 octet electrons from oxygen times 3 gave us 18. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. And you'll notice that I went ahead and I started out on the outside ones. I spread them out around as best as I could. I got to the end, and I ended up short. I didn't have enough electrons to finish oxygen. So we're going to have to make a double bond. So which one do you want to put a double bond on? You might say to yourself, well, it doesn't really matter. It's the same on both sides. What if I go ahead and I specify that this particular one is going to be an isotope of oxygen? Oxygen's atomic weight is going to be 16, but maybe there's an isotope that's 15 or 17. I'll just go ahead and call this one O15. Better way to do that, what if we just put a star here specifying that this one happens to be an isotope? Boy, now it's not so symmetric anymore, is it? Now it actually does matter how we build this thing. So I'm going to go ahead and leave this labeled for the moment. That's actually what we like to call it. If we have one where we've deliberately made one of these spots an isotope and the other ones aren't, we usually say that the isotopic one is going to be labeled. So I can either go ahead and erase that pair and draw it right here to get a second bond, or I can go ahead and bring it from this side, make the double bond on this side. Notice that these are two different structures, right? The labeled one here has a double bond, the labeled one down here doesn't. So which one is right? The answer is they're both right simultaneously. It's going to have the electrons sometimes spending more time right in here. Other times, the electrons are going to be spending more time right in here. So something really neat is happening here. What we're saying is both of these are right, and remember, since the electron is moving around at the speed of, close to the speed of light, we're going to see that it's going to interconvert between these two forms. Now, that seems like a bigger deal than it actually is, because remember, all that we're saying is that we have two electrons that happen to be in this region, then they happen to shoot over here and spend some time over in this region, and so it's just interconverting back and forth. Well, here's something we can do to help communicate that. Now, let me give you a caution. What you see right here is a snapshot, like a photo finish instantaneous photo of what ozone looked like. This is a different one of what the same ozone molecule looked like, just at two different moments where the electrons happen to be in different spots. We can count the electrons up really well in these cases. But if you want to use this notation, don't try to count your octet here because that can cause some problems for you. So what I'm going to do is I'm going to go ahead and draw a third version. Now I'm going to go ahead and I'm going to omit the extra pairs that are there for the moment because I want to communicate something. If I'm saying that half of the time there's a bond that's right here, a second bond that's here, the other half of the time there's a second bond that's over here, well, it's like I'm saying that there's 1.5 bonds here and 1.5 bonds here. So my bond order for what I call a resonance form is going to be a bond order of 1.5 instead of 1 or 2. It's in both places simultaneously. Now if I go ahead and I show those two pairs that we would still have, and we're going to have a third pair somewhere. See, now it gets really complicated. Where do we put that extra electron set? Things get very weird, which is why usually we don't draw the electron pairs when we're doing a resonance structure. We want to count our resonance structure's octet whenever we're in one of the two snapshots. Don't do it when we're in this form. But here's something that's really cool about this. It seems like it's just some sort of a weird bookkeeping trick to say this is a 1.5 order bond. But actually, that really is the case. I mean, if I were to take the bond length of a single bond and the bond length of a double bond, it turns out these bonds are actually going to be about halfway between those two sizes. The strength is going to be pretty close to halfway between them. All these things are going to be true about the ozone molecule. So remember, the word for this is called a resonance form. Now, what we can do to communicate that these are doing the same and they're interconverting, we can do a single arrow between them that's double-headed like this. It turns out in chemistry we care a lot about the way you draw arrows. So this is going to be one of your first arrows. Make sure you're drawing it correctly. It's a pretty obvious one, but it's going to be subtle when it shows some other arrows later in the semester.